at Yale University, and today I'll be talking about resolving cold gas streams across cosmic scale with Arepo and Gamma 2, a brand new simulation effort with collaborators listed down here. And then from the title, the key is cold gas streams. And to just motivate a bit more, I would like to start with a statement that I hope everyone here would agree, that all stars form out of cold gas. So to make the observable universe, here's the data from DESI. The bare-bone pipeline will look something similar to this. We start out with cold gas demographics. So where and how is the cold gas distributed in a universe? What are the structures of cold gas? And then also is cold gas multi-phase, clone B, or both? And we couple that with star formation physics to produce the visible stars and galaxies, right? And in the past 2 or 3 decades, much attention of the community has been kind of given to developing star formation subgroup models in physics. Ask the question, how well do we actually understand cold gas demographics? And then the answer might be surprising to some. We actually don't know a whole lot about it, for reasons that observationally is very challenging to map out cold gas because its intrinsic faintness. And simulation predictions are probably not as robust as many people would think, because we actually have not reached numerical convergence in many of the cold gas kind of demographics. And then to just illustrate the later point, so here on the left, I'm showing the gas density of a Milky Way size system from the Arepo simulations. And then so what you're seeing, kind of the inner blurry hue, that's the inner ISM. And then the outer warmer hue, that's the CGM of the halo. So if we run the same simulation, so this is using the standard mass-based refinement criteria as in TNG. So if we rerun the same simulation, but right now, we're just kind of additionally introducing uniform 1 kiloparsec refinement across the CGM. You can kind of, while fitting everything else the same, you can see kind of visually, there's an emergence of many more small-scale warm and cold gas structures by the virtue of just adding in more resolution elements. And I would also like to bring out this quote from the Illustrative TNG public release paper, really recognizes still one of the core issues with the current simulation suite is that they still don't have the resolution to properly resolve the ISM. And so he is really just calling for the need to resolve cold gas across cosmic scales. And obviously this is a kind of multi-scale problem, so we are kind of approaching this whole process in kind of divide and conquer approach. So on the left, I'm showing the filaments, intergalactic filaments, connecting the nodal galaxies. So nodal galaxies are those massive galaxies with real masses of 10 to 11.5 to 12, redshift of 3 and above. So on the left, we have these kind of structures happening on megaparsec scales, where the typical cooling length at 10 to the 4 Kelvin is about 1 kBc or lower. And so we have kind of dedicated zoom-in suites trying to capture all those physics led by Zhuang and Nier. And then as these cold gas streams kind of approaching one of such nodal galaxies and puncturing through the hot CGM halo, we are working with kind of structures on hundreds of kiloparsec scales, where the typical cooling length right now is of 100 parsec or lower. And then we have kind of separate dedicated suites led by Isa and Daisuke, and these are run with the Arepo code. And as these streams kind of making their way towards the ISM of these nodal galaxies, we have kind of separate idealized simulations that are really trying to capture physical processes and structures happening on parsec scale. And then these are done with using the code Gamma 2. So on very high level, for part A and B, we have cosmological zooming simulations. They're hyper refined on illustrative TNG. And then on the very far end on the right, we have idealized simulations. Okay? So for part A, here we are really trying to resolve the multi-phase nature of intergalactic and circumgalactic medium. So here the plot is showing a phase-on view of a cosmic sheet. And then individual circles are denoting the virial radius of individual halos. So there are 2 things I would like you to know. The first one is there are kind of preferentially a lot more kind of low mass systems forming along the visible cold gas filaments. Secondly, there are a lot of small-scale kind of warm cold cloudlets forming kind of around these filaments and also around the CGNs or these nodal galaxies. So the key questions we're kind of after here is we want to understand the demographics, dynamics, and also the structure of these intergalactic filaments. And secondly, for these kind of lower mass systems living along the filaments, what's the impact of environmental quenching on these low mass galaxies? And thirdly, the fact that these intergalactic medians are multi-phase, what does that say or imply on the Lyman alpha measurements and inferences? And so to do that, we kind of identify massive nodal galaxy pairs, and then we crop out the kind of the spheres and then connecting cylinders at ratio of around 2, and then extend that out to 1.50 radius of the more massive nodal galaxy. And we crop out that entire volume and then trace that back to ratio of 127, find the entire Lagrange volume, and then resolve that with uniform 250 parsec co-moving resolution. And so we will have 5 such zooming simulations of filament connected nodal galaxy pairs running from redshift 7 to 2 with about 35 snapshots for each of them. Okay? So as we're kind of approaching one of such nodal galaxies, here's an example from the Leisure TNG 50. And Isa will be talking a bit more about that after this talk. And then the outer circle is marking 3 times the viewer radius of the system, so roughly the boundary of CGN of the system. And to kind of shed a bit more light, a bit more on the gas dynamics here, we are looking at the radial mass flux map where we see clear outflow of hot gas, and you also see 3 quite pronounced dense cold gas kind of rushing towards the center of this system. And then the question here is, can we properly understand the physics within CGN? And also how much can we trust those predictions within the simulation box? And then to be a bit more precise, we are interested in the structure, demographics, and importantly, the numerical convergence of these cold gas streams. And then in particular, we are very interested in the question of how deep do these streams go into this hot CGN halo. And then for a reason that they are bringing in the fresh supply of cold gas to sustain and fuel the very high star formation rate cosmic noon. And currently, there is no agreement among existing cosmological simulations for the kind of resolution related kind of concerns. And lastly, we really want to resolve the very complex but very interesting cold gas inflow and CGN interactions, which includes processes like Helmholtz instabilities, real shocks, cooling, self-gravity and self-shielding of the stream, magnetic fields, and gravitational confinement. And so to do that, we identify these nodal galaxies featuring prominent inflowing streams, and then we crop out the CGN and apply uniform 50 parsec co-moving resolution across the entire area. And this constitutes a huge kind of step forward compared to the previous 250 parsec resolution IPN simulation I showed in the previous slide, and also kind of the typical 1 kiloparsec resolution around the CGN of these massive nodal galaxies. So we will have about 20 of such zoom-in simulations of nodal galaxies featuring prominent streams going from redshift 3 to 2, and with about 70 snapshots each, such that the string sound crossing times resolve with about 20 snapshots. Okay? Lastly, as we make it our way, kind of sprinting to the final mile of the marathon, as these streams making their way through the central ISN, the questions we are asking, or we are after here is, with these supply of cold gas streams, how does that impact and sustain star formation, driving turbulence, and then how are these physical processes all tied together to the overall disk formation evolution picture? And so here is a typical kind of simulation would look like. So on the top, I'm showing the face-on view of the disk, stellar disk structure. And on the bottom, I'm showing the cold gas disk component. And you'll see there are 3 wedges here where we manually introduce coherent cold gas streams into the simulation box. And as we evolve the system further, you can see very clear coevolution between the cold gas disk and also the stellar disk component. And so this process is very complex and rich. So we approach this problem from kind of 4 different orthogonal angles. The first one is we want to understand how do these coal gas streams impact the turbulence life cycle within ISM. So we want to understand the turbulence power spectrum localization using tracer particles, and then also what sources these turbulence, whether that's stream impact, radiative processes, or star formation feedback. And then more importantly, the numerical conversions of these properties. Secondly, we want to understand how do these streams drive local star formation and protoclump formation. So protoclumps are these compressed node turbulence supported high density coal gas structures. And then they are the future forming sites for star clusters. So just to illustrate, so here is one of the snapshots from the simulation. So in the bottom, where you see there are not or over densities or high concentration of coal gas, you kind of see kind of corresponding in the same spatial location, there are over densities of stars. And thirdly, we want to understand kind of what's the role of streams in impacting and shaping the global dynamics of this. In particular, we want to understand what's the role of the stream play in the angular momentum acquisition of the disks as a function of different configurations of these streams. And lastly, going back to the gas, we want to understand what are the properties, sizes, velocities, dispersions, and other kind of properties of the kind of parsec scale coal gas structures. And for metals, when they are generated after kind of star formation, how are their transport across or within the simulation box or within ISM are impacted as different function of different string configurations. And then the goal here is to inform us to build, hopefully, a redshift dependent disk evolution model. So to do that, how are we going to do that? So this is kind of a typical gas disk and then inner ISM. So we apply uniform 3 parsec resolution physical, because idealized simulations, cropping out the entire inner ISM. And then we're doing this using the code Gamer 2, whose GPU acceleration kind of feature allows us to make these very expensive simulations more computationally accessible. And then so in a simulation box, we manually introduce 3 strings. And then the key physical parameters here we want to explore is the impact parameter B, and also the string mass flux. And then, because again, this is a very intrinsically complex process, so one of the strong suits of idealized simulations is you can really turn on different physical processes one by one. That are otherwise not possible in cosmological simulations. So we have a 3-tier kind of simulation kind of design where in the first tier, the simplest possible case, we are running non-radiative simulations where all the temperature variations purely caused by adiabatic contraction and expansion. And then we introduce radiative processes where we have a fixed UV background redshift 3 and include primordial cooling. And then at the end, we kind of bring in everything, star formation. They are kind of calibrated to the Agora Cosmo run. So this is in calibration with Yuri Oku that have integrated the Osaka feedback model into Gamer. And then so this is also kind of very different regime and resolution. So we also, at the same time, in the simulation group, there are also people running parsec resolution on dwarf scale, which is more accessible to understand the numerics and calibration of these star formation models. So I will stop right here to take questions. Yeah.
Okay. Do we have quick questions for Barry?
Thanks, very, very interesting talk. I'm curious, you may have mentioned this and I may have missed this, but fragmentation of coal, does that play a big role in this?
Yes, so Isa, I assume you're referring to the coal gas streams, the properties of coal gas stream within CGN.
Sure, yeah.
So she will be talking a little bit more about that. I think right now the key uncertainty is we actually don't really know what they look like when they if they make it all the way to the central ice, and what are the physical properties. Likely clumpy, Well, the reason that it's difficult to say now is, so with the laser TNG of kind of 1 kiloparsec resolution, you're only resolving the cold gas stream with 1 to 4 cells in diameter, which is probably dominated by numerics. And then so the reason we're also starting out with smooth string, not because it's more physical, but it's because it's more clean. Because you can always add additional layer of complexity afterwards. Yeah. Okay. Let me.
Okay, I suggest we have Isabel get set up. If there's any last question for Barry. Otherwise, that's that. Oh, I see one from Phil at the back.
So, of course, no simulation can capture all the kind of, this is all the way to kind of subatomic scale. But the hope is at some point, for instance, if we see there's a conversion scene, because we also be doing some resolution tests and stuff. So, say, the size distribution of cold gas clouds, at least we can see whether above the resolution limit, are we getting conversions on the size distribution, say, as a function of other physical properties. We don't know yet. But I think that's a hope. If at some point we can resolve down to at least get the structures to a spatial scale of interest that's relevant for, say, in the bulk of the physics, I think that would be great. But we don't know. I think the question is we don't know. But that's a hope.
Okay, thanks very much, Barry.